Hello students, in this video we will be learning about what is molecular orbital theory. Now we shall start explaining the formation of each and every molecule. First one, hydrogen. Hydrogen is formed by the combination of two hydrogen atoms, that is, one hydrogen atom is having 1s1 configuration. The next hydrogen is also having 1s1 configuration. When they combine together, they result in two types of molecular orbitals, sigma 1s and sigma star 1s. So what is sigma 1s? This is got by the addition of the wave functions a and b. That is the first case and the second case. The second one is obtained by the addition of the additive inverse of the second wave function to that of the first one. How shall we explain that? Total number of electrons in the molecule it is 2. We have learned that the capacity of each and every molecular orbital is 2. Now we shall write the molecular orbital configuration. We know that the lowest molecular orbital, that is sigma 1s, and how many electrons are there occupied? 2. So this is the configuration. Now to find out whether the molecule is stable or not, we use a quantity that is known as bond order. Bond order is calculated using the formula half of number of electrons in bonding minus number of electrons in antibonding. Now here in this case you find that only bonding orbitals are involved, and how many electrons are there? 2 electrons. So what will be the bond order? It is half of 2 minus 0. That means the bond order is 1. The integral values of the bond order indicates the number of bonds in between. So here you find that the bond order is 1. That means hydrogen has a single bond in the molecule. Now we shall check the molecular orbital diagram for this. We are going to represent the energy level diagram for the molecule hydrogen. So first of all, this is the way in which the energy increases. Now if you take the first atom has 1s1 configuration. Here you have 1 electron left. So similarly, the next orbital is also having 1 electron, that is in 1s1. Both of them are having almost comparable energies and symmetries. When they combine in two different manners. One which is actually got by the combination of the wave functions, that is known as the bonding type, that is marked as sigma 1s. And how many electrons are there? 1 electron comes from this side and 1 electron comes from the other atom, and we have sigma 1s 2. So this is the molecular orbital. So the one which is represented at the side, that is the atomic orbitals, and the one which is represented in the middle, that is known as the molecular orbital. How many types of molecular orbitals are formed by this combination? You find that there are two types. One is known as sigma 1s, the other one is known as sigma star 1s. So sigma star 1s is having relatively higher energy, but here you find that it is unoccupied. Since the bond order in the molecule is 1, if it is positive, we can say that the molecule formed is stable. Now, to check the nature of this molecule, we have to check how many electrons are there in the molecule, whether it is in the paired condition or not. If it is in the paired condition, you find that when a magnet is brought near the substance, it gets repelled away. That is, such substances which have only paired electrons in them, they have a tendency to repel away the magnet, and such substances are known as diamagnetic substance. So what did you understand in the case of hydrogen molecule? Hydrogen molecule is diatomic in nature. This diatomic molecule has 2 electrons that is occupying the bonding molecular orbital. It has the molecular orbital configuration of sigma 1s2, and so you find that the bond order, when calculated, we get it as an integral value. That means we have a single covalent bond in between, and we have seen that it is having only paired electrons in the molecule. With the result, it is repelling away the magnet, and so it is diamagnetic. Hope it is clear. The next example that we are discussing here is beryllium molecule. We want to check whether the beryllium molecule exists or not. For that, first identify what is the Z value for beryllium. Z is 2, that is atomic number is 2. So we find that 2 beryllium atoms, if taken, we have the configuration for them as 1s2 and 1s2. How many total electrons are there? Here you find that there are 4 electrons. So total number of electrons in the molecule is 4. Now, what is the molecular orbital configuration? So, I am writing it as MOC, molecular orbital configuration. First, we begin with the lowest molecular orbital, that is, which is having the lowest energy, sigma 1s. We arrange 2 electrons there. Next, go to the higher level, that is sigma star 1s2. Now, calculate the bond order. What is a bond order? How is it calculated? It is calculated using the formula half of number of electrons in the bonding molecular orbital minus number of electrons in the anti-bonding molecular orbitals. Here you find that 2 electrons are present in the bonding as well as the anti-bonding molecular orbital, from which we can understand that the bond order will be reduced to half of 2 minus 2, which is equal to 0. That means that their bond order is 0, or you say that there is no bond existing between the molecule. That means that beryllium molecule doesn't exist. Hope you have understood. Now, let us check the case of carbon, whether carbon will form the molecule. Carbon, we write it as C2 molecule. What is the atomic number of carbon? Z value is 6. What is the electronic configuration? We have the configuration for carbon as 1s2, 2s2, 2p2. Similarly, the next carbon will also have 1s2, 2s2, 2p2. Total number of electrons in the molecule. How many electrons are there? You can find that it is 2 into 6. That means 12 electrons are to be arranged. Now we'll check what will be the molecular orbital configuration. We begin with sigma 1s. So we have the configuration sigma 1s 2. Next higher level is sigma star 1s2. Then comes sigma 2s2, sigma star 2s2, which is the next higher orbital. We have arranged 8 electrons in them. What is left over is 4 number of electrons. So these 4 electrons are to be arranged to the next higher level. The next higher level, you find that the bonding molecular orbitals like pi to px equal to pi to py orbitals are present. So these are degenerate orbitals, each having an occupancy of 2. That means total of 2 plus 2, 4 electrons can be occupied. So then this is the molecular orbital configuration. On calculating the bond order, we get half of Nb minus Na will be written as half of, how many bonding electrons are there? 2 plus 2 plus 2 plus 2. Total of 8 electrons are there, minus, here we have 2 electrons in the antibonding. This is also yet another antibonding, total of 4 electrons. So then it becomes bond order is found to be 2. That means the molecule is stable. So if the bond order is positive, we can conclude that the molecule will be a stable one, and we also have integral value. That means carbon will have a double bond in between the molecule. Now we shall draw the molecular orbital diagram. Coming to the energy level diagram of molecular orbitals in carbon, first we represent the atomic orbitals of the first carbon on one side and the second carbon on the other side. So we have first case 1s, 2, then we have 2s, 2. The next higher orbital will be 2p, 2. 2p2. Similarly, on the other side, I have the orbitals of the second carbon, which is of comparable energy. First one, 1s2. Then we have 2s2. And the next higher level will be 2p2. When it combines, it results in the molecular orbitals 1s combining with the second 1s to form the bonding type, that is sigma 1s, and the next one sigma star 1s followed by 2s, which forms sigma 2s, sigma star 2s, followed by the next higher level, that is pi to px, pi to py, both are degenerate. Then comes sigma to pz, followed by pi star to px, pi star to py. And finally, what we have is sigma star to pz. Okay, we shall name it. This one will be pi to px, pi to py. This is sigma to pz, followed by pi star to px, pi star to py, and finally sigma star to pz. Now we shall fill up the different molecular orbitals. So first case, you find 1s2 and 1s2. When they are having 4 electrons, you find that this molecular orbitals are completely occupied. So you have 1s sigma 1s2, sigma star 1s2. Likewise, sigma 2s2, sigma star 2s2. Now how many electrons are left over in the p orbitals? We have total of 4 electrons. So these 4 electrons are to be filled up in the lowest molecular orbital, and it follows the Hund's rule. So it has to be filled up like it is half filled first and then it gets paired up. So you have total of 2, 4, 6, 8, 10 and 12 electrons. So you find that on checking the configuration, you find that only paired electrons are there. That means the molecule is diamagnetic in nature. That is, when it is brought near a magnet, it will be repelled away by the magnet. So carbon molecule is diamagnetic in nature.